Chapter 4A, Confidence Intervals and Central Limit Theorem. In this activity, we're going to start thinking about statistical judgment and how we can apply and use statistics to draw conclusions. Make sure you've read through why we're studying this, the learning objectives, and our new vocabulary for Chapter 4. Chapter 4 is a longer chapter, so it's broken up into parts A and B. Part A has a lot of examples, so this is broken up into 2 videos. And this video will cover examples 1 through 4. So you'll see some of the familiar concepts, but some new formulas in here. We're going to be working with population proportions that correspond with categorical data, so you'll notice the formulas look a little different than our standard deviation formula for quantitative data. So example 1 investigates color proportions for M&Ms, and there's a video about watching how Mars makes M&Ms that you can watch. I'll link to this in our Canvas page. So one of the employees at the factory in Hackettstown claims that all M&M factories in the U.S. produce an equal number of each of the 6 colors of M&Ms. So we will investigate this claim in our discussion question. Since it's not practical for us to visit each M&M factory in the U.S., we use sample data and sampling techniques to investigate. So think about, we want to investigate if the proportion of blue M&Ms in a random sample of M&M candies is equal to the proportions of the other colors. So we want to think about what types of results are going to support the factory employee's claim. So we say if there are equal amounts of the 6 colors, this supports the employee claim. If we find an unusually large amount of blue M&Ms or an unusually small amount of blue M&Ms, then there are problems with the employee's claim. Since we're interested in predicting the proportion of blue M&Ms, this is categorical data. So our variable x here that represents the color is a categorical variable. The population for this activity is all US M&Ms because if you look back to how the employee made the claim, the employee's claim is that all M&Ms factories in the US produce these equal numbers of each of the 6 colors. So in most cases, statisticians cannot know the population proportion. For example, if we're surveying people about their political opinions, we can only use survey data. We don't know how everyone in the whole population feels. In this situation, the M&M factory employee is making a claim about the parameter, which is the population proportion for each color. So according to the M&M factory employee, we want to think about what is the population proportion that we'll call P for blue M&M candies. We use P for proportion here. So if all 6 colors are equal, then the proportion that we expect of blue M&Ms is 1 out of 6. So we say the population proportion for the claim is 1 out of 6. Each student starts with a sample of 10 M&Ms. So in this case, in the video, I'm going to talk through how you do it. If we have class time, we'll do it in class. If not, you're welcome to get a pack of M&Ms and randomly count out 10 M&Ms and record the amount of blues in your packet. So each student is going to have a different value if they randomly count out 10 M&Ms and then count the numbers that are blue and then find the proportion. The proportions will range from 0, which would be a student who had no blue, to 1, which would be a student who had all 10 out of 10 M&Ms blue. That would be very unusual, I think, to have 10 out of 10 M&Ms blue. So, is the proportion of blue M&Ms from your individual sample a reasonable estimator for the proportion of blue M&Ms coming from all factories in the U.S.? So since we expect variability in sampling, an individual sample is not a reasonable estimator. We know just by chance one sample might be different. Now, if you think back to the law of large numbers that we discussed last activity, the law of large numbers says if we do very many samples, we expect to see a pattern. So we expect there to be some variability in samples, meaning that the proportions in a sample are going to be different from the parameter, that's the population value. But overall, things should not be surprisingly different. So to get a reasonable sense for the parameter, we use a dot plot to look at the proportion of blue M&Ms. So this is from a class I taught last semester, And students figured out their proportion of blue M&Ms and then put this dot plot up here. So here we see there's definitely a peak at 0.1. That would be 1 out of 10 M&Ms were blue. And that's close to the 1 out of 6, or 0.01667 as a decimal. But we also here have a peak at 0.3 in this class data. If we did different dot plots for different classes, they would all be slightly different, right? Because of variability in sampling. So we want to think about how could we construct a computer simulation to sample the color proportions for M&Ms. So this page describes the directions for StatCrunch. I'm going to head over to StatCrunch and you can follow along. So this is a list of sample proportion of blue M&Ms from students in fall 2016. They counted them out by hand for me. So we're going to go into applets and we're going to choose sampling distributions. And then we're going to use data from the data table and we're going to select our column here, the sample proportion of blue M&Ms. And when we click compute, this sets up a sampling applet for us. So up here in the top graph is the population distribution. So this is similar to the dot plot that would have been drawn by this fall 2016 class. And we see the mean of their dot plot is 0.2061. The median, the middle value, is 0.2. And then we've got what we call the unadjusted standard deviation because that includes outliers. Like this value may or may not be an outlier, but it looks like it might be. To know for sure it's an outlier, we would do a statistical calculation like you did in earlier chapters. So let's watch what happens if I click one time. So here in my samples graph in the middle, the computer randomly drew two values, and one came from this column and the other one came from this column, plotted them here, and then took their average or mean and also their median and plotted that down here. This last graph is a graph of the sample means. So now we'll do it again. You can watch. It's another two random points. In this case, it looked like they worked out to be from the same columns. If we do it again, you can see now we're picking two different points at random. Columns like these in the middle that have lots of values are going to be randomly chosen from more often because there's more data there. Let's watch if we do this 5 times now. So notice we're starting to get a graph here of the sample means, and then we get a mean of the sample means that's right around 0.1688. Notice the sample size is 2. We're pulling out 2 values at a time and averaging those 2 values. So each time we do this, we're going to get different results because it's a computer simulation. So you could try it with this data file at home or write down your own random draws of M&Ms and create your own data file and try it. So now we've left the sample size at 2. We clicked 1 time, we clicked 5 times a few times. Now let's go try and have the computer simulate this 1,000 times for us. So if we do this 1,000 times, we don't get a nice animation because that would take a long time. But we do get a distribution showing the sample means for a sample size of 2. And so of these values, the mean of the sample means is 0.2075, and the median, the most frequent value, is 0.2. I'm not surprised because looking at the original graph, the median was 0.2 and the mean 0.2061 was awfully close to this mean here. If I click 1,000 times again and I do 1,000 more samples, notice the mean changes a little bit. And we've done 2008 samples altogether, meaning we drew 2 values from here, averaged them, plotted them 2008 times with the help of the computer simulation. So in the notes, these are different values than we have here because of variability in sampling. So these are values that I got when I recorded these notes here. So they're close to what we saw, but not exactly the same due to variability in sampling. So now in part B, we want to adjust the sample size to be sample size 3 and see if that makes any changes. So I'm going to change my sample size to 3 here. We start over. We still got the same population that we're drawing from. That was the data from my fall 2016 class. And if I draw one sample, notice now it pulled 3 different values out of that population distribution and average them. If we do it 5 times, we can watch the animation. And we see our mean and our median are a little bit higher than before. So let's do it 1,000 times now. And we see our mean, it's still a little bit higher, but it's closer to our previous results, 0.2091. Let's do it 1,000 more times. So now we've got 2,006 different sample draws of size 3. And here's the mean that we got here. If you compare this to what I recorded here, it's a little bit different, but still in the same range. And that's due to variability in sampling and the data set that I was using. These came from different groups of students sampling M&Ms. So now in class, there'd probably be around 32 students. So let's go look and see what happens if we change our sample size to 32 instead of just thinking about averaging 2 or 3 draws. And let's see, if we do it 5 times, it pulls 32 values here, 5 different times and plots them for us. And then we start to get a graph here. If we do 5 times again, we can start to see the sample means graph forming. And if we do it 1,000 times, we see this graph is a lot tighter, because imagine what happens if you're drawing 32 values. Even if one of those values is an outlier out here, when you're averaging that far out value with 31 other values, most of those values come from the center or the cluster in the population distribution. So when you're averaging 32 values, that dampens the effect of outliers. So notice this graph here is much tighter around the center at 0.2 or thereabouts. If you look back, the standard deviation also changed. So remember, before our standard deviation was right around 0.14, and now look, when we are averaging 32 values, the standard deviation is 0.258, which is showing us the narrowing of this distribution. It's getting more compressed because averaging 32 values, the outliers aren't going to be included in such an average. So we see similar results when I did the simulation in these notes. The center is still about 0.2, but we see the spread is narrower. That's the big difference. When you have a larger sample, your averages get closer together. So we want to think about, based on the results of our sampling distribution, is there good evidence to support the M&M Factory's employees' claim that all M&M factories in the U.S. produce an equal amount or an equal number of each of the 6 colors? So we say the mean and the median after simulation are close to 0.2, which is not too far from 0.1667, which is 1/6 as a decimal. It could be true, but we're still not sure. So let's continue our investigation. So in our previous simulation, we saw that the sample proportions graph was lopsided, like the population graph, until the sample size got very large. Let me take you back there and show you again. So here, when we've got a sample size of 32, we see this is normally shaped. If we go back to when we had a sample size of 3, notice this sample means distribution does have a right tail similar to the population graph. If we adjusted it to be, 15, we see, all right, it's closer to normal, but we still got a little bit of a right tail or a right skew there. Let's see if we put it at 10. Notice it's got a little more spread and the skew is more pronounced. If we went all the way up to, say, 40 sample size, we see a pretty normal symmetric shaped sample means graph. And that's because, remember, the outliers in an average of 40 different values aren't going to have as much weight on the final calculation. Most of the values are going to come from the part of the graph that contains most of the data. So if we have a large enough sample size and repeat the number of samples many times, like we did 1,000 in the simulation, the histogram looks almost like a normal distribution curve. So in order to use the normal distribution approximation, the rule of thumb is that the sample size times the population proportion must be at least 10, meaning you've got to have a chance of probability times the sample size be about 10, meaning it's got to occur about 10 times or more. So similarly, we want the sample size times 1 minus the proportion to also be at least 10. So as formulas, we write n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. Remember, p is the probability in this case of a blue M&M. So 1 minus p, that would be 5 out of 6, or the probability or proportion of another color M&Ms. Some statisticians say at least 15 instead of at least 10. We're going to use 10 as our rule of thumb this semester, but don't be surprised if you look at another textbook and see those statisticians recommend using at least 15. So this rule of thumb is sometimes called the rule of sample proportions. So when we did our first trial, we had n is 10. Let's look, what if we did n is 20 for our data here, and p is 1 out of 6, still the proportion of blue M&Ms. If we check 20 times 1 out of 6, 20 out of 6, that is 3.33. That's not 10. We wouldn't expect at least 10 blue M&Ms. So we wouldn't want to use a sample size of 20. We want more data than that to get approximately normal results. So n times 1 minus p, 20 times 5 out of 6 is big enough, but because n times p is not big enough, we can't use a normal approximation. So let's check, what if we go up to n equals 40 as our sample size? 40 times 1 out of 6, our n times p calculation is 6.667. So again, it's not up to 10, even though n times 1 minus p, the 40 times 5 out of 6, is greater than 10. Both of these calculations have to be at least 10. So then if we let n be 60, meaning our sample size would be 60 different M&Ms we'd pull out of the bag, n times p is exactly 10. So we're in business here. For more sureness in your results, you could go to n equals 80 or n equals 100, depending on how many M&Ms you have, so that these would be a reasonable random sample. So we're going to go with n equals 60 because it's just barely large enough that n times p is 10, and we're able to use a normal approximation. So you could do this at home, or if we have class time, we'll do it in class together. I'm going to use data here from when I previously did this with a class last semester. But you would randomly count out 60 M&M candies. And when I say random, make sure that you're not looking at the candies, you're not biased in any way, you don't turn your head away or close your eyes. We're still going to investigate the proportion of blue M&Ms, so X is still the variable representing color. So our population is going to be all M&Ms in the US, as before. But now our sample, instead of being 10 M&Ms, is 60 M&Ms that are on your plate. And then you can record what proportion of your 60 M&Ms are blue. Each student should have a different value, or, don't expect to have the same value as your neighbor. You may or may not. So then we could do a dot plot of a whole class values. On the next page, I've gone ahead and done the standard deviation calculation. So you can think about, a dot plot, we'd expect it to be centered close to 0.2 or 0.1 if the population proportion really is 1/6. So using the fact that the population proportion is 1/6 and that our sample size n is 60, we can calculate the standard deviation. So the standard deviation here is 1 out of 6, and then we're going to multiply that by 1 minus p, which is going to be 1 minus 1 out of 6, or 5 out of 6 here. And then we divide that by the sample size 60 and take the square root at the end. So we get our standard deviation here is about 0.048, or if we round it to the hundredths place, that would be 0.05 rounded. So using the population proportion, 1 out of 6 is the center. So we treat what we expect to be the population proportion as the center of the normal distribution. I wrote it as a decimal, 0.167 here. We can use the standard deviation to fill this in. I use 3 decimal places here. You could use 2 decimal places. So we add up 0.048 with each standard deviation, and then we go down. So if we had a p hat, a sample proportion of blue M&Ms 0.2, that would be right here between the center and 1 standard deviation. So a p hat of 0.2 would not be unusual because we are within 1 standard deviation. We wouldn't be surprised to have results like that. So using this p hat 0.2 that came from a group in my class last semester, we can calculate exactly how many standard deviations that is. So our Z formula here, in the numerator, we're going to say statistic minus parameter. In this case, the statistic is the P with the hat, the sample proportion, minus our population value divided by the standard deviation that we calculated up above. So P hat here was 12 out of 60. I believe this came from one of the groups in the class last semester. That works out to be 0.2. So if we do our Z-score calculation to figure out how many standard deviations away this is, 0.2 minus 0.167 gives us a positive 0.033. We divide by the standard deviation, and we get 0.06875, a little bit above the mean, but within positive 1 standard deviation. So most sample proportions, we could say usually about 95%, fall within 2 standard deviations of the center. So does this sample proportion for this particular group fall within 2 standard deviations? So this group that had their p hat equal 12 out of 60 is 0.2 blue M&Ms was not unusual. They were within 2 standard deviations. If you run this yourself, you could do it a few different times to check and see, are your results within 2 standard deviations, or are you getting something unusual? If you're getting values way out here or way down here, more often than not, then you would start to doubt that the population value really is centered at 1 out of 6, the 0.167 as a decimal. So from this class, last semester, these are the different p-hats from their groups. Notice they're all out of 60 because our denominator here was 60 M&Ms per pile, randomly selected, and then the numerator's counting the blues in those groups. So you can see there's quite a bit of variability between the different groups in class. So let's think about what if we combine all of our blue M&Ms into one p-hat blue value for the whole class. So there were 9 different groups here, so we can check 9 times 60 is 540 total M&Ms. And then if we add up all these numerators, in this class I had total 140 blue M&Ms. So we can make a whole class p-hat, 140 divided by 540, and we get 0.259. So that's a little higher than that p-hat of 0.2 that the other group had when we pool the whole class data. So let's think about how many standard deviations is this value away from the center. So again, we do our statistic minus parameter in the numerator. So we're going to say our statistic is 0.259 minus 1 out of 6, or 0.167 as a decimal. We get 0.092, right, because this is above, higher than the population proportion. And then we divide by 0.048, and we get 1.91 standard deviations. So this is further out than that previous value we looked at from just one group. So now in StatCrunch, we can go to the normal calculator and figure out how much area is there to the left of our p-hat value, which was 0.259, assuming the distribution is centered at 1 out of 6, or 0.167. So I'm going to close our applet out and go to Stat, Calculators, back to the normal calculator. And now we want our mean to be 0.1667, or 0.167, and our standard deviation was 0.048. I'll just go to 3 decimal places in here. And then we want to know what's the proportion of values less than, was that 0.259 in our sample data. And we see 97% of the data is less than that. And then if you want to see our 68, 95, 99.7 ticks, remember you can click on that. And this should look very similar, give or take rounding, to the sketch that we've got on the previous page. So we see the area to the left is 0.972, meaning 97.2% of the values would be less than our class value. The area to the right, we can say 1 minus this area using the complement calculations is 0.028, meaning we expect around 2.8% of the trials to be higher than that. So is this unusual? You can think about roughly 2 standard deviations as unusual, because that would be less than a 5% chance. So you'd have 2.5% in each tail if you look back at your chart for the 68, 95, 99.7% rule. So these results are close to 2 standard deviations away from the center, but they're not quite over 2 standard deviations. Remember, we were at 1.9 standard deviations. So we're suspicious, but we're not certain that the blue M&Ms are more than 1/6 of the proportion. So we're going to now construct confidence intervals. This is another tool that we use to make predictions. So remember from our probability unit last chapter that approximately 68% of the observations fall within 1 standard deviation, approximately 95% of the observations fall within 2 standard deviations, and approximately 99.7% of the observations fall within 3 standard deviations. So here is data from a survey at LMC. So professors at LMC would like to estimate the proportion of statistics students at California community colleges who are also taking English. So as a project, they surveyed 320 students currently enrolled in statistics. And we don't know too much about their sampling methods, but we'll assume, since they say at LMC or another school, that they were surveying students who attended different community colleges than just LMC. So of those, 207 were in an English class, and 113 were not in an English class, and those add up to 320 total. So we want the sample proportion for the number of yes responses. So this 207 out of 320 is our p-hat. As a decimal, is 0.6469. If you wanted to make it a percent, you could say 64.69%. So this is our value from our survey. Since it was a pretty large survey, 320 people, we expect it to be close to the population proportion, but we know due to variety and variability and sampling that this is not what we expect the exact population value to be. So we want to check to make sure, do we have enough data? Do we have at least 10 responses in each category? And just eyeballing, I can see, I had 207 yeses and 113 nos. Since this is just a yes or no question, I know I definitely had 10 responses in each category. You can work through the calculations. N times p-hat, 320 times 0.6469. That gives you the 207, which is definitely greater than or equal to 10. So we can check and say that one's okay. If we do n times 1 minus p-hat, that's the 320 times 1 minus our probability. That's 113, also greater than 10. So we can check that off. So since both calculations are greater than 10, a normal model is appropriate and we have enough data. And I put a note here. Notice that the rounded calculations match the counts of yes or no in the table of the responses in the survey. So if you're working with to-answer survey questions like this, it's sufficient to check to make sure, do I have at least 10 responses in each category? So in this case, we don't know the population parameter. So we want to estimate the standard deviation. So we call this the standard error equation. It uses statistics instead of population values. So we're going to use p-hat instead of p here. N is still the total number in the survey. So p-hat is 0.6469. N is 320. We can work through this calculation for the standard error. We multiply, divide, and then square root at the end, and we get 0.0267 as our standard error. The standard error is going to measure how much the graph is stretched or compressed, the graph of the normal distribution, stretched or compressed. In the same way that the standard deviation does, the difference is that the sample error comes from sample data. The formula for quantitative data, the standard error formula, is a little bit different than the standard deviation formula to make up for the fact that a sample might not include extremely high or extremely low values. For proportions, the formula looks almost exactly the same, except we've got p-hat instead of p. So our goal is to estimate a population proportion. So we want to try to make an estimate that falls within 2 standard errors of the center. And so using that fact, we construct what we call a 95% confidence interval. So I start with the sample proportion, and then I'm going to add and subtract 2 standard errors to get a range of possible values that I think the actual population value might lie in. So we've got here our sample proportion, 0.6469, and this symbol's plus or minus, meaning we're going to go through two operations. 2 times 0.0267, if we multiply this out, we get 0.0534. So you can check in your calculator, 0.06469 minus 0.0534 gives us 0.5935. This is our lower bound, which is 59.35%. The upper bound comes from adding, so we take our 0.6469 plus 0.0534, and we get 0.7003 or 70.03%. So how do we interpret this? So here is one way that we can interpret our interval. We can say we are 95% confident that between 59.35% and 70.03% of all California community college students enrolled in a statistics course are also enrolled in an English course. So what are salient features of our interpretation? First, our 95% is how confident we are in our methods or how confident we are in our answer. It's not saying 95% of the time this or that happens. It's saying 95% is how sure we are in the methods that we used. Here I used the percents to report out. You could have also used the proportion values. It doesn't matter whether you use a decimal or a percent. And the other important feature here is that our prediction is about all California community college students. We already know about these 320 students in the sample, so they would not be who we're making the prediction about. Our prediction is about the whole population of California community college students. So it's important to make that very clear that you're predicting about the population value, what we call a parameter, in your interpretation. Here's another way you might interpret. You could say the confidence interval is the success rate of the method that produces the interval. To say that we are 95% confident the unknown proportion lies between 0.5935 and 0.7003 is shorthand for we got these numbers using a method that gives correct results 95% of the time. So when you write out confidence intervals, you want to use one of these structures to explain the meaning of your interval. It's important that you explain that we're predicting about the population proportion for all California community college students. You can choose as a user the confidence level. Typically we choose 90% or higher because we want to be quite sure of our conclusions. So let's think about what a 68% confidence interval would look like. Remember, 68% corresponds with one standard deviation. So this is 0.6469 plus just one standard deviation here. We get 0.6202 as our lower bound from subtracting and 0.6736 as our upper bound from adding. So as a statement, we can say we are 68% confident in our methods that between 62.02% and 67.36% of community college students in statistics are enrolled in English also. So again, we're predicting about all community college students, and that 68% is confidence in our method, not anything to do with the sample students. So now what if we want to be 99.7% confident? That corresponds with 3 standard deviations. So notice in the calculation, now we're multiplying the standard deviation of standard error, whichever value you're using. In this case, it's the standard error, I believe, right? Because it comes from sample data. So we multiply that by 3. We call this the margin of error when we've multiplied the standard error or the standard deviation by however many standard deviations or standard errors we're counting. So here we can say our p-hat value, our statistic, 0.6469, plus or minus the 0.0801, which came from multiplying our standard error times 3. Subtracting, we find the lower bound is 0.5668, and the upper bound is 0.727 after rounding. So notice this is wider than our 68% interval estimate because we're more confident in our answer. So if we're more confident in our answer, then we need more room for error or a larger margin of error. So we can say as a statement that we are 99.7% confident in our methods that between 56.68% and 72.7% of community college students in statistics are also enrolled in English. So again, our prediction is about all community college students, the population value. And again, that 99.7% is how confident we are in our methods. So question F asks us to think about which confidence interval is widest. So we see clearly from our calculations that 99.7% interval is widest since it includes 3 standard errors, right? It goes lower than the other intervals and it goes higher than the other intervals. So that makes it a wider interval. So we trade off higher confidence in our methods for a wider interval. So if we want to be more sure, there has to be more possible population values.